The purpose of the lube filter is to promote long system life by keeping damaging contaminants away from sensitive engine components. To better understand how a filter works, let's look at the components of a typical spin-on filter. The primary components are a base plate assembly, a bottom end cap, a center tube, the filter media, a top end cap, a compression spring, and a can. Oil enters here, is filtered through the media, passes through the center tube, and into the engine. The name bypass may be misleading. Partial flow is actually more descriptive. In a bypass system, about 10% of the oil flow is finely filtered and returned to the sump where it sweetens the dirty oil. It is a continual process in which all of the oil is filtered within minutes. With the full flow system, developed in the 1950s, 100% of the oil is filtered before it reaches the bearings. Therefore, the filter is less restrictive and more free-flowing than a bypass filter and should remove all particles large enough to cause immediate damage. If the system becomes too restrictive, the engine may not get enough oil. Because it is better to get unfiltered oil rather than no oil at all, full-flow systems utilize bypass or safety valves that open under OEM-specified differential pressures. The bypass valve is located in either the system head or in the filter itself. In the 1960s, the full-flow and bypass systems were used together. This hybrid system offers benefits of both without some of their disadvantages. With this method, all oil is continuously filtered by the full-flow filter before it reaches the engine's critical components. About 10% of the oil is diverted to the bypass filter where it is scrubbed of fine contaminants. Oil from the bypass filter is returned to the sump. The use of a bypass filter will lengthen the service life of the full-flow filter because the bypass filter removes additional contaminants that could plug the full-flow filter. A significant breakthrough in filter systems came in 1987 with the development of the combination full-flow bypass filter. It combines both elements within one filter canister. It is easier to service than two individual filters and results in lower maintenance costs. Remember though, with the combination filter, there is usually less oil in the system and some decrease in contaminant capacity, which lessens the margin of safety. Recently, Baldwin introduced its line of high-velocity, dual-flow spin-on filters. High-velocity filters have one inlet and one outlet. All oil flowing through the filter is sent directly to the engine to protect vital engine components, rather than a portion being returned to the sump as with conventional dual-flow filters. When selecting a filter, it is important to note and understand performance ratings. Overall performance is expressed through micron ratings, beta ratios, efficiency, and capacity. A filter's micron rating is the measurement of the size of contaminant that can be efficiently captured by the filter. Filters typically trap contaminants in the 5 to 20 micron range. While microscopic in size, these contaminants can cause extreme damage to the engine. Remember, something as small as a human hair is 50 microns. Beta ratio describes how efficient a filter is in trapping particles of a certain size. A multi-pass test is used to count the number of particles of a given size before and after fluid passes through a filter. This information is converted into the beta ratio using this formula. In this example, at the 10 micron level, the number of particles upstream is 2,000. This number is divided by the number of particles downstream, which is 1,000. So at the 10 micron level, the beta ratio is 2. Efficiency is then calculated by taking the beta ratio minus 1 divided by the beta ratio. This number is multiplied times 100. In this example, the efficiency is 50%. This is a nominal efficiency rating. Efficiency is largely determined by the filter media. Media that is more restrictive will filter out more and smaller particles, thus giving the filter higher efficiency. That same restrictive media, however, will lower the filter's capacity. Capacity is the amount of contaminants the filter media can hold before the pores begin to plug, interrupting proper oil flow through the filter. Highly restrictive media that increases efficiency allows less oil flow and, as a result, decreases capacity. So, as efficiency increases, capacity decreases. Therefore, a filter with high capacity will have less efficiency. Because of this, filters must be capable of removing the damaging particles while still allowing for proper oil flow. Understanding the correlation between capacity and efficiency is important when selecting the proper filter. A high efficiency rating with low capacity could result in frequent change intervals. On the other hand, high capacity with low efficiency may lead to engine failure because less of the damaging contaminants are captured. Often a middle ground between efficiency and capacity is the best place to be. When comparing like products from different filter manufacturers, request comparative test results from standardized tests.